Okay. Okay, so it's my pleasure to introduce Arman Darbinyan from Texas A&M. He's going to talk about embeddings into left-orderable simple groups. Arman.
Thank you, Funda. Thank you for introduction, and thank you for having me in your seminar. So yeah, as the title suggests, I'm going to talk about subgroups of left-orderable groups. And here, mostly I will concentrate on left-orderable simple groups, but not only. So I will mention some recent advancement in the subject, but as you will see from my talk, I will mostly view all these advancements from the viewpoint of combinatorial and geometric group theorists. So let us start from the very basics. I would like to recall the most traditional definition of left-orderable groups. So basically, you are given a group, and we will mostly in this talk consider finitely generated groups, but in few instances we'll also consider countable groups, so not necessarily finitely generated countable groups. So when G is a countable group, then linear order that is defined on the group is called left order for the group G, simply if it is being preserved by the left multiplication of the elements of the group. So there are some alternative definitions of this fact. So one of alternative definitions, which is going into a little bit more set theoretical setting, says that the group is left orderable if there exists a partition of G by sets P negative, P positive, and the unit element, so that P negative is the inverse of P positive. In this case, it corresponds to the situation when P positive is the set of so-called positive cons, meaning the elements that are larger than the unit element with respect to the given order. And since there is like this recent advancement in group theory about a counterexample of Kaplansky's unit conjecture, I would like to mention that one reason why, one of many reasons actually why left-orderable groups are interesting, because the structural properties they provide help us to answer some open questions about groups. So for example, we have this property that says that left-orderable groups, they satisfy unique product property, and because of that, they also satisfy Kaplansky's unit conjecture, but also Kaplansky's zero conjecture, by the way. There are some other definitions, equivalent definitions of left-orderable groups when it comes about countable case. So some of these definitions are in more topological setting. For example, one can characterize all countable left-orderable groups as the ones that are embedded into the orientation-preserving homeomorphisms of the real line. And the proof of this fact, even though it seems to be somehow different from the previous definitions, the fact is easy to prove. It actually is based on idea of first embedding the group G into the set of rational numbers, so that this embedding is bijective embeddings that respects the order of the group G. And then once you have this bijection, this embedding rho phi that is defined here, it actually provides you the necessary, the desirable embedding of the group G into the homomorphism preserving, into the orientation preserving homeomorphisms of the real line. I would like to mention that once you move from the case of countable groups to the case of groups of cardinality continuum, then this is not true anymore. And some examples were constructed by Catherine Mann. So there are some other constructions by Cristobal Rivas, which I forgot to mention in my slides. But yes, so this is very sensitive towards the cardinality, which should be countable. So there are some other properties of left-orderable or bi-orderable groups that I would like to mention that will provide more context for the next results that I'm going to mention. The first one is about bi-orderable groups. And here I forgot to mention what is bi-orderable group, but probably the name already suggests the definition. It is a group that has a linear order that is stable under left and right multiplications at the same time. So not only left multiplication, but also right multiplication. And when we move from the class of left-orderable groups to bi-orderable groups, we want to know how much are different the borders of these two classes. How much bi-orderable groups can be different from left-orderable groups. So one of the theorems about bi-orderable groups that is a classic and was mentioned by Levy in his article of 1942, it says that bi-orderable groups are locally indicable, which immediately means that there doesn't exist any finitely generated simple bi-orderable groups. A more recent result is by Witten-Morris that says that the same conclusion, the same property also holds when we consider left-orderable and also amenable group. So these two properties, amenability and left-orderability, leads us to the same conclusion. So these two theorems make it interesting to see, can actually it be so that there exist, in fact, left-orderable simple finitely generated groups? And the answer to this question is positive. Yes, it exists. And the discovery was done quite recently by Hyde and Lodha, who constructed actually a continuum family of left-orderable simple finitely generated groups up to isomorphism. And in fact, these ideas of Hyde and Lodha later were shown to be prolific in finding some other exotic properties of left-orderable groups. For example, among such groups, there exist left-orderable groups whose every continuous action on the circle has a fixed point. This was also an open question that becomes very interesting in the context of classification of actions of left-orderable groups. And this was shown actually based on the constructions of Hyde-Lodha and on modifications of this construction by Matteo and Tristino. Again, recently, some other exotic properties of these groups include, for example, the fact that among them there are groups that are uniformly perfect, which means that each element of the group can be presented by a fixed number of commutator elements. In fact, there exist cases when each element of the group is a product of 3 commutator elements. So this is also an exotic property, but not of topological or dynamic flavor, but this time it's more algebraic flavor. So what's interesting about this class of finitely generated left-orderable simple groups is that one can combine different contexts into this subject. And this is actually the goal of my talk, to show that the context one can input into this framework goes actually even outside of topology dynamics or geometry, and it can touch even like some very classical topics that relate to logic and algorithmic properties, computability properties, etc. So in order to do that, of course, I would like to go into some history. Before mentioning the history, I would like also to mention the main motivating theme for me. So the main questions that I want to touch in this talk is about what groups can be subgroups of finitely generated simple left-orderable groups, and what properties, what relationships between these subgroups and overgroups can exist. So when we talk about subgroups and overgroups, of course, we can translate this terminology into the terminology of group embeddings as it is formulated in my slides. And before going into some new results in this direction, I would like to mention some very classical results that are asking the same question, but in the context of not in this restrictive context of simple and at the same time left-orderable groups, but in a broader context of, for example, left-orderable groups. And here we have a very classical result of Neumann that says actually every countable left-orderable group embeds into a finitely generated left-orderable group. And of course, the part that it says the countable group is left orderable, it cannot be improved because we know that every subgroup of a left orderable group must be left orderable. Actually, a more recent result that is in the same topic as in the same spirit as the result of Neumann was obtained by Bluetooth-Glass, who actually moved from the realm of finitely generated group to the subclass of finitely presented groups and obtained a similar result, but this time the embedding is in the finitely presented group. So basically Bluetooth and Glass, they constructed Hickman type embeddings, but for the class of left-orderable groups. So similar question when it is asked about simple groups, again, has a very old history, and actually again it was shown that there is no restriction on the subgroup of finitely generated simple groups, except the fact that they must be countable, and the theorem of Hall that was later also recovered by Gorushkin and Shub using different methods says that every countable group actually has an isomorphic copy inside finitely generated simple group. So here I would like to mention that these four results that I mentioned of Neumann, Hall, Gorushkin, and Shub, they capture basically all this classical tool set of embeddings into finitely generated groups. Namely, when we talk about results of Neumann and Hall, then the constructions that they provide, they are based on risk product structures on groups. And when we talk about results of Gorushkin and Shub, then these results, they use what is called free structures, some of the main tool sets that exist in combinatorial group theory. But there's also another result of embeddings that actually not just says that a group is a subgroup of a simple, finitely generated simple group, but it also provides some structure of structural relationship between the subgroup and the overgroup. So here I'm talking about a famous result of Thompson from 1981 that says that every finitely generated group, Fratini embeds into a finitely generated simple group, such that it also preserves the word problem of the initial group. So why it is interesting fact that it preserves the word problem, I will discuss a little bit later. In fact, it is connected with some, it has some important connections with the result of Boone and Hickman. But also I would like to stop here on the fact that it is a Fratini embedding. So what is Fratini embedding? In literature, actually, Fratini, this terminology of Fratini embedding has another name. It is called conjugacy stable embedding or conjugacy stable subgroup. So what it means that the sub elements of the subgroup are conjugate in the overgroup if and only if they are conjugate in the subgroup itself. So the overgroup doesn't add any new conjugation of elements of the subgroup. So if you talk in a little bit metaphorical terms, then it means that the overgroup, in this case, the overgroup is denoted by G, it somehow knows what elements of H are conjugated. Because if G knows everything about itself, then it knows that if elements of H are conjugate in G, then it must be that they are conjugate in H and vice versa. So this is kind of a rigidity result in algebraic sense. And of course, it preserves the word problem. It is already another context. It's a more logical or computational computability theory context. But one other remarkable thing about this Thompson's theorem is that this embedding result uses quite novel ideas. Now they are also classical ideas because they are related to the famous Thompson's groups and actions on the counter spaces. But at the time it was done, it was a novel idea. Talking about embeddings that preserve some extra properties, some structural properties, I would like also to mention geometric embeddings. And one of these classical topics about embeddings that preserves the geometry is so-called quasi-isometric embeddings. So basically what it means that the embedding is quasi-isometric, it means that the geometry of the subgroup that sits inside the overgroup, in this term notations, it is G, the overgroup is G and the subgroup is H, or vice versa, the subgroup is G and the overgroup is H. It means that when we view the group G as a geometric object via its Cayley graph, and we view through the metric that provides the group H through its own word metric, then it doesn't distort much the geometry of G when it is viewed through the word metric of the group G itself. So more formally, it is written here what it means. So this is also a result which can be translated in a more metaphorical terms by saying that the overgroup can recognize or can know the geometry of its subgroup, assuming that the group G knows everything about itself. So, and one result of this type, the quasi-isometric embedding result that I would like to mention is a result of Brightson. It says if a class of finitely generated groups is closed under isometric amalgamations along three subgroups, then every group from this class can be quasi-isometrically embedded in a group that has no proper subgroup of finite index. So in particular, when it says no subgroup of finite index, obviously, like every simple group has this property. So this also provides some context why it might be interesting to consider also this type of geometric embeddings into finitely generated simple groups. So here are the promised context about why it is interesting that Thompson's group preserves the word problem. It is basically related to the characterization of groups with decidable word problem that is given by Boone and Higman. And this characterization says that given a finitely generated group, then it has decidable word problem if and only if it has an isometric copy as a subgroup of a simple subgroup of a finitely presented group. So what is remarkable about this characterization is that first it considers property, meaning decidability of the word problems, that belongs to the logic, belongs to the computability theory, but then once it is considered in the setting of the groups, then it can be translated into a language that is more in geometric group theory or combinatorial group theory or even algebraic terms. It uses the words finite presentation and simple subgroup. And Thompson's theorem actually makes this result stronger in the following way. So the theorems that I mentioned here, I call it Hickman-Boone and Thompson theorem. Actually, the first version of Hickman-Boone, it was obtained in the 1970s, and the result of Thompson comes from 1981. So here, the contribution of Thompson is that actually this simple subgroup can be chosen to be finitely generated. So it actually makes a noticeable contribution to the philosophy of this type of results, because one thing that is worthwhile about this type of results is that we are bringing some computability logic properties into a more finitistic terminology that is coming from group theory. So, considering that results, actually Bludov and Glass, they moved from the context of just finitely generated groups to the context of finitely generated left-orderable groups, and we managed to obtain results that are of the type of Boone-Hickman's result, but in the context of this time left-orderable groups. However, their results didn't manage to capture the property that the simple subgroup is finitely generated in the sense of a Boone-Hickman theorems that I already mentioned. And it leads to this natural question. So is it true that every finitely generated left-orderable group with decidable word problem is embeddable, I missed the word is, into a finitely generated left-orderable simple group that also has decidable word problem? So all these topics, all these theorems are actually a motivation for us to consider the question of what groups are subgroups of finitely generated simple left-orderable groups. And here I would like to mention the first result in this direction, motivated by this context, that is the results that we obtained with Markus Steenbock. Steenbock, it's a quite recent result. It says that, first of all, there is no restriction on the class of subgroups of finitely generated left-orderable simple groups, besides the fact that these subgroups should be countable and left-orderable. And of course, these restrictions cannot be removed for obvious reason. But it also says that if we consider embeddings of groups into these finitely generated simple left-orderable groups, then in fact, it can preserve some structural properties in the fashion mentioned above. Namely, these embeddings can be made Fratini embeddings. These embeddings can preserve computability properties. For example, if the group G has computable left order, then the overgroup H also has computable left order. Interestingly, if G is finitely generated, then such embeddings can be made to be isometric. So isometric in the sense that the metric of the subgroup with respect to the word metric of the overgroup coincides with the metric of the subgroup itself. And here I would like to make a small comment, actually important comment. When we talk about isometric embeddings, we have to carefully choose the generators. because isometric embedding is with respect to the generators of the subgroup and overgroup. So it's important. But otherwise, if we don't carefully choose the generators, then we can make sure that with respect to any word metric, the embedding is quasi-isometric, but not necessarily isometric. So another consequence of the results is actually a partial answer to the above mentioned question of that we attribute to Glass. It says that the finitely generated group with a recursively enumerable left order has decidable word problem if and only if it is a subgroup of a finitely generated simple subgroup. When I say subgroup, of course, I mean that there exists an isomorphic copy inside the finitely generated simple subgroup of a finitely presented left-orderable group. So in this way, we obtain a strengthening in the similar fashion that Thompson obtained the strengthening of Boone-Hickman's theorem. So I would like also to mention that geometric embeddings were unknown not only into the finitely generated simple left-orderable groups, but they were until recently unknown for finitely generated simple groups as well. And so a positive answer in that direction was obtained recently independently by me and Steenbock and Belk and Zaremski, that says that in fact every finitely generated group quasi-isometrically embeds into a finitely generated simple group. So so these embeddings, quasi-isometric embeddings, also can be made isometric embeddings if we carefully choose the generators. And one other consequence of the results that I mentioned above, again, goes into this setting, the classical setting of combinatorial group theory. It considers a natural question of can the characterization of Boone-Hickman and Thompson of groups with decidable word problem be made also so that these embeddings are geometric embeddings. They respect the word metric. And the consequence of the results that we obtained is that given a finitely generated group has decidable word problem, if and only if it quasi-isometrically, and here the contribution is that it is quasi-isometric embedding, so it quasi-isometrically embeds into a quasi-isometrically embedded finitely generated simple subgroup of a finitely presented group. So what is nice about or interesting about this theorem, it puts more context into the theorem. So first we have the context of coming from logic, that is this decidability word problem. Then we have the context of simple groups embedded into finitely generated, finitely presented groups that brings more combinatorial group theory context into it. But when we also respect the geometry of the embedding, it becomes more also, it brings also a geometric context into this characterization. So things that I also would like to mention some other strengthenings of some known results, which unfortunately somehow disappeared from my slides. Don't know how it happened, but so I will make some comments, or maybe I can actually write it here. If you consider a countable family of finitely generated groups, so let me write it here. So G is a countable family of finitely generated groups. So let us consider finitely generated left-orderable groups. So it will bring to another result. Then the theorem says the following. So there exists a finitely generated left-orderable simple group that we denote by H, such that each of groups G that belongs to this countable collection of groups quasi-isometrically embeds into H. So what's interesting about this theorem is that it says for any countable collection of finitely generated left-orderable groups, there exists a universal group that is finitely generated left-orderable and simple, so that the groups from this collection embed, not just embed into H, but they embed geometrically. And the interesting part here is that they embed actually geometrically. And in fact, one can actually remove these restrictions that the groups are left-orderable in these two instances. Also, one can consider more computational contexts within this theorem. Namely, if also we put a restriction on this collection G by saying that it's a recursively enumerable collection of groups with decidable word problem, then again, such a universal group H will exist with additional property that H will have decidable word problem. And here I would like to mention that once we move to the case of collection of groups with decidable word problem, then one cannot avoid the restrictions that the collection is recursively enumerable, because otherwise it is known that such a universal group H doesn't exist. So that result would be the strongest possible result in this context. So mentioning all these theorems, now I would like to briefly go and sketch some ideas about how these constructions can be obtained. This is my next slide. Actually, these embedding constructions have different layers. So the first layer is when we start with our initial countable and let's say left-orderable group, when we consider the results that touch the left-orderable case. And the first step is to bring these left-orderable groups into finitely generated left-orderable groups, because we feel more comfortable in working with finitely generated case. So the first step is just to bring into finitely generated groups. And this first step can be done by using some classical tools that were known already at the time of Philippe Hall, for example. But then once you make this embedding and you already have your group G1, then the next step is already containing some novelty, and it is embedding the group G1 into another group G2, which is not necessarily simple, but it is a perfect group and also left-orderable. So I would like to recall what is the definition of simple perfect group. Perfect group simply means that it coincides with its commutator subgroup, with its derived subgroup. So it is known that obviously every simple group is a perfect group, but not vice versa. And only once you have this embedding into the perfect group, Now you can consider the final step, which is about embedding into the group with desirable properties, namely the group H that is finitely generated, simple left orderable, and also preserves all the structural properties mentioned above. So here, one natural question one might ask is why we need this intermediate step of embedding into perfect groups. And here the answer is that because these constructions, starting from step number 2, they use some dynamical and topological setting in which, for simplicity, we use some arguments that consider group actions on nice topological spaces. Namely, among such criteria of simplicity, the ones that we utilize is the classical criterion of Upstein that says that if you are given Y as a Hausdorff space on which G acts faithfully, then for N being a normal subgroup of H, if there exists a non-trivial element G of N and a non-empty subset U of Y, such that G completely moves U, so that the intersection of the image under the action of G on U doesn't intersect with U, then the commutator group RU with RU is a subgroup of N. Here in this statement, I forgot to mention what is RU. RU is a so-called rigid stabilizer. It means all the elements of the group G that act trivially outside of the set U. So this criteria actually is of central importance in order to show that
H is the H the same as G.
So let me see. Oh yes, sorry. So in this theorem, yes, I have another inaccuracy. So instead of H, it was supposed to be G. Thank you for noticing that. So it was supposed to be G, of course. Yes. And so this property plays an important role for us. That's why actually we need to have this to be perfect subgroup, so that it will tell us that this commutator subgroup actually coincides with N. So one more thing that we used in our construction is actually the constructions that was built by Mattebon and Trestino. And so I will draw this construction, but before drawing, I would like to introduce the setting. So we are given the set A, the Cantor set, basically, with which is the infinite product of the set of zeros and one employed with the product topology. So, and then we act on it by shifts. So we get a dynamical system, a shift system. And then we consider a subshift of that system that is minimal. And once you have this setting, I would like to draw this setting actually. Oops. So you have your set X here. X is a subset of A. It's an infinite subset. And here you take the Cartesian product of X with R. Then you define on this space an equivalence relation that is given as here. So you just take this point, glue this point where the distance between this point with respect to the R coordinate system is equal to 1, and 1 point is obtained from the other point by the action of phi, by the left or right shift, as you want. So after you take this equivalence relation and take the factor space of this Cartesian product, you obtain what is called, so basically it's a compactification, and this is called a mapping torus, or a so-called suspension space. So I will make some picture of it. So maybe it's not the best picture, but what is interesting about this picture is that once you consider these fibers, so these fibers are somehow being twisted around it. But it preserves a lot of important properties from the initial space, and this is of key importance for us. For example, in this initial space of Cartesian product, you have a natural ordering. You can first order these points of the x-axis, and then consider some lexicographical argument to take to consider ordering of any homeomorphism of this Cartesian product, so that this homeomorphism translate points from the fibers to another point on the fiber. So it preserves the fibers. So once you have it, you can make an and this translation should be orientation preserving on each fiber. So meaning that the restriction of the homeomorphisms that we are interested in about this Cartesian product, they should be actually orientation preserving homeomorphisms when of the real line when restricted to each fiber, so that they have natural order that comes from the order of homeo plus R. And then once you order the elements of this set X by some lexicographical argument, you have a natural order of all homeomorphisms of this products that have these additional properties that they act orientation preservingly on these fibers. Now, what is remarkable about this setting is the following. So let us consider some charts that we call diatical charts. So what I mean by diatical chart? So in this picture, it's rectangle. So this way it is easy to visualize what I'm going to say. So let us consider a projection of this rectangle on the x-axis, so that this projection is a Kloppen set. And let's consider this projection on the r-axis, so that this projection is it's an interval of length strictly less than 1, but also the endpoints of the interval, they are diatical points. So this interval becomes a dyadic interval of length strictly less than 1. Then let us consider homeomorphisms of the type that I already mentioned that are defined as follows. So you consider these fibers of the rectangle, and you consider homeomorphisms of x times r that act on these fibers as elements of the Thompsons group F. Just to remind you what is Thompsons group F. So if you consider this unit square of sides 1 and 1, then it is the set of all continuous maps that have slopes being powers of 2, and with continuous maps such that the breakpoints actually diadical points. So something like this. So the breakpoints, by the way, you have finitely many breakpoints that are diatical points, and the slopes are powers of 2. So F has some remarkable properties. One of the properties is that F is finitely presented, but also the derived subgroup of F, that is FF, it is simple and left-orderable. Somehow these properties are of key importance. So then you act on these fibers as elements of F. So once you have all the collections of these homeomorphisms, then of course, once you jump from this space to this factor space, this suspension space or mapping torus, then you have induced homeomorphisms on this space. And in fact, one can show that the order that is defined on the initial space, it will be preserved in the suspension space. But what is even more remarkable, the set of all collections of these homeomorphisms, once projected to this suspension space, they compose a group that is simple and finitely generated. So this is, and these homeomorphisms that are induced from the homeomorphism coming from this product space, they are called, the collection of them is the group T-phi that was defined by Mattebon and Tristino, and the theorem of Mattebon and Tristino says actually that T-phi is finitely generated, simple, and left-orderable. So this group actually plays an important, this idea actually plays an important role for us, because somehow we extend this idea to consider some other homeomorphisms as well. So one of the ideas for which I don't have time to go into details, but we have also a technical lemma which must be also incorporated with the ideas described above. So this lemma that we call modified dynamical realization, that actually embeds every left-orderable countable group into the orientation preserving homeomorphisms of the real line, or in our setting, it is not just the real line, but the 0-1 interval. One has to modify also that embedding by putting some structural restrictions on this embedding, on which I wouldn't like to go deeper, because this result is technical. But this is why, because of this result, that we have all these structural properties that are being preserved by these embeddings. So I hope that I gave some general idea, and probably I should stop here, and would be happy for your questions. Thank you.
Well, thank you. Thank you very much, Arman.